In our seventh section on our very long 8-section talk on water, we're going to be looking at municipal waste. How do we treat that? The 3 levels of quality associated with municipal waste. We'll talk about natural wastewater treatment, and we'll also talk about remediation. And so this is kind of a fun topic because we're using containment, extraction, and biological treatment. So we're going to use organisms to treat our water. Hopefully you're seeing a theme throughout all of these videos, and that is rather than having to remove and treat water and remove pollution from the water, the cheapest and most effective way to reduce pollution is to avoid producing it and releasing it in the first place. We know that eliminating lead from gasoline has resulted in a widespread and significant decrease in the amount of lead in U.S. surface waters. We still have work to do on that. We know that we actually need about 10% of road de-icing salt that we are using right now. So 90% of the salt we use on roads in the wintertime doesn't even need to be used. If we were to reduce it to about 10% of our current usage, we would still not affect the safety of our roads. So roads would still be safe just by removing that. We also know that reducing or handling our oil and petroleum products a little more carefully can reduce the amount of water pollution caused by these materials as well. Industry plays a really big role in this. As you know, industrial pollution can be on a bigger scale than domestic production of pollution. And industry can reduce pollution by recycling or reclaiming materials that otherwise might be discarded into our waste stream. So if we use this approach and you have a company who is able to extract a valuable metal or a valuable chemical and then turn around and sell those to somebody else who needs them rather than releasing them as a toxic contaminant, it's a lot more economical and it's a lot better for the environment as well. As we've discussed before, non-point sources of pollution are harder to control than point sources because we don't exactly know the source of the pollution in a non-point source pollutant. Farmers, as we continually talk about, have long contributed a huge share of water pollution. This includes sedimentation, fertilizers and pesticides, and all of that is resulting from runoff from the fields. However, if we can use soil conservation practices to help keep the soil and contaminants on the fields where they belong, where they're needed, we can do this by asking our farmers to apply precisely the fertilizer, the irrigation water, and the pesticides. So if they're able to keep this on the field, that's not only going to save farmers money, but it's also going to reduce water contamination. So that's like the big goal. We can also ask to preserve wetlands. Remember that wetlands are going to help to capture sediment, so it stops the sediment flow into larger streams and rivers and lakes. But it's also going to capture contaminants, and it helps to ultimately protect surface and groundwaters. If we're in an urban area, we're really looking at reducing waste that enters storm sewers in order to prevent those non-point sources of pollution. The tremendous challenge of managing these sources is seen in the Chesapeake Bay. So in the Chesapeake Bay, we had nutrient pollution. It degraded the bay pretty seriously by the 1970s. However, citizens groups, local communities, state legislators, everybody came together and established an innovative pollution control program that made it one of the first estuaries in America that was targeted for not only protection from pollution, but also restoration measures. Some of the objectives of the plan was to first reduce nutrient loading. We know that that leads to eutrophication and massive die-offs of marine populations. They did this through land use regulations. They controlled agricultural as well as urban runoff. They upgraded wastewater treatment systems and plants, and they improved compliance regarding discharge. So what are we sending out? What is an allowable amount of pollution that we're sending into the waterway, and requesting that permits be filed in order to discharge. So at this point, these prevention measures have been successful, and replacing wetlands as well as planting seagrasses has also helped to remediate this particular area. All right, let's talk about municipal waste. Under natural conditions, water purification can occur constantly in both soil and water. Bacteria are going to take up and transform nutrients. They can also work to break down oils. We know that as water moves through sand and soil, this can filter the water. We also know that plant roots and fungi can use nutrients that are found in the water, so that prevents our nutrient loading. And they can simultaneously capture metals, say heavy metals that would be considered a contaminant in water, and other components. However, when you get a high population density, say such as in a city, you're going to produce a lot more waste than your natural systems can process. So this becomes less of an option that can be used. Most developed countries require that cities and towns build municipal water treatment systems to purify human and household waste. As we've already talked about, human and animal waste usually create the most serious health-related water pollution problems. There are more than 500 types of disease-causing or pathogenic bacteria and viruses and parasites that can travel from human and animal excrement through the water. Most rural households use septic systems. So this is going to allow solids to settle in a tank. The bacteria will decompose them. The liquids are going to percolate through the soil, where we are hoping that there's not an overload, but the soil bacteria can presumably purify those. So this is a really good option when your population densities aren't too high. It is an effective method of waste disposal. But with urban sprawl, groundwater pollution often becomes a problem because you're overwhelming this system. All right, when you are treating wastewater, a municipal wastewater treatment plant is going to have 3 different levels of quality. We alluded to this in our first slide. Sanitary engineers have developed ingenious and effective municipal wastewater treatment systems. So in primary treatment, you're going to physically separate your large solids from the waste stream. You're going to use screens and filters and settling tanks to do this. So you're separating into a solid at the bottom and liquid on top. In secondary treatment, you're going to use aerobic bacteria or bacteria that require oxygen to break down dissolved organic compounds. So these guys are kind of acting like your decomposers in a natural setting. And although the wastewater is usually free of pathogens and organic material after secondary treatment, it still is going to contain high levels of inorganic nutrients, which is where your tertiary treatment comes in. In a tertiary treatment, you're going to remove dissolved metals, nutrients, especially nitrates and phosphates. And if you remember back to a couple sections ago, this is really important to remove nitrates and phosphates because those are going to stimulate algal blooms. Those are the things that can lead to eutrophication or nutrient loading in a not only a marine but also in a wetland area, or say if it got into a lake or a pond, you're going to wind up with algal blooms, which can kill off all the other organisms that are living in that environment. Sewage sludge, that's the solids left over, it can be a valuable fertilizer. But it can be unsafe if it has metals or toxic chemicals or pathogens if it came from humans. Some cities will take this sludge or biosolid and use it on farms and forest lands. Some cities will convert that sludge to methane and use it as natural gas to heat homes and to power, I guess furnaces are heating homes. A lot of cities, though, will take that biosolid, that sludge, and they'll either incinerate it or they're going to throw it in a landfill. Remember, in primary treatment, you have a settling tank where you have filters that allow your solids to separate from your liquids. The center picture that you're seeing right here is going to be a high pressure aeration tank where you're going to have your aerobic bacteria digesting all of those organic materials and starting to break them down, very similar to what you would see in nature. So we talked about the 3 levels of municipal water treatment. However, conventional treatment, as what we described, is going to miss some of our newer pollutants. In 2002, the USGS released the first ever study of pharmaceuticals and hormones in streams. Scientists were able to sample 130 streams, and they were essentially looking for only 95 contaminants. These contaminants included things like antibiotics, natural and synthetic hormones, detergents, plasticizers, insecticides, fire retardants, all of these things that humans have produced and are starting to, what they thought was potentially contaminate waterways. All of these substances were in fact found in low concentrations. One stream, for example, had 38 of the compounds tested. at the time, our drinking water standards only existed for about 14 of the 95 substances that they tested for. So these are just things that we're kind of discovering are present. We didn't know they were present before, and they're starting to get into our waterways. A similar study found that the same substances in groundwater, they were finding the exact same substances, and this is alarming because, as you know, groundwater is a lot harder to clean than surface water. So questions that scientists are asking now are, what are the effects of these widely used chemicals on our environment? What is it doing to the environment? What is it doing to the people who are consuming water? We're not entirely sure yet, but that would be the first question that we'd ask ourselves as we're starting to fill gaps in our knowledge and then figure out what does distribution of contaminants look like, and then therefore how can we prevent the spread of those contaminants through our watersheds. Jumping off of our last slide discussion on some of these unusual contaminants, we are now able, it's not that they weren't there before, it's that we're now able to test for these pollutants, so we're able to actually detect them in surface waters. Some of the more unusual pollutants that we're finding in surface water, and I apologize, we're going to write this down real quick. This is being measured in micrograms per liter. So small amounts, but enough to be detected. And again, we just don't know what the effects are in the environment. So we're finding things like steroids in water. That was one of the highest frequency materials, non-prescription drugs, insect repellents like DEET, detergent metabolites. So we have to be real careful that we're not pumping phosphates into the environment. Disinfectants is a pretty high rate as well per liter. I worry about disinfectants, specifically triclosan. Triclosan was recently banned as an antibacterial agent. It was found in every antibacterial soap because it works so well. And I think primarily, Bath and Body Works was the last to voluntarily ban triclosan. It is now a banned substance. But the problem with triclosan is that it persists in the environment, and that it persists in water specifically. It travels through water. This is a hormone disruptor for aquatic life, and it has a cumulative effect. Because it doesn't break down very easily, it's going to stick around, it's going to persist in the environment. So we just don't know what long-term effects of, even though we banned it now, we don't know what the long-term effects are of having that triclosan in the environment. Some other unusual pollutants that we're finding are antibiotics, fire retardants, caffeine is showing up a lot more, and other prescription drugs too are making their way into our watershed. So we've talked a lot about municipal wastewater treatment. These facilities are great in an urban setting, but they're really expensive. So an alternative to that is going to be a natural waste or an alternative waste treatment system. These are better for places that are remote, that don't have a lot of money for infrastructure to build these huge wastewater treatment plants. The benefits of an alternative waste treatment system is that they are going to take less energy. They use gravity and plants and bacteria to naturally clean the water, so it's not requiring a huge influx of energy for that. What you're looking at here is called a constructed wetland. It's where you take artificial marshes designed to filter and decompose waste. So you're kind of using what the environment does already, but it's in a more controlled setting. This particular alternative waste treatment system is coming to us from Cedar Grove Cheese Factory, and they call it their living machine. It's a sequence of tanks, bacteria, algae, and small artificial wetlands, and the goal is to convert factory effluent to nearly pure water and wetland flowers. So this system alone is able to handle 99% of the biological oxygen demand. It removes 98% of suspended solids, 93% of nitrogen, and 57% of phosphorus. So it's a really effective alternative. So as we're kind of seeing, there are a lot of different sources of water contamination. However, we're starting to kind of see that there's a lot of different options and solutions to clean it up. There's been some new developments in environmental engineering, and these are providing some pretty promising developments and solutions to water pollution. For example, we can use bioremediation. This involves containment, extraction, or biological treatment. So a lot of times we can actually use living organisms to clean contaminated water. This is effective and it's also inexpensive, and this is called bioremediation. So we're using living things to remediate a polluted water source. Restored wetlands along stream banks or lake margins can effectively filter out sediment and remove pollutants. So just leaving wetlands there or returning wetlands to an area close to a stream can help to remove pollutants in of itself. Some plants are very efficient at taking up heavy metals and organic contaminants. So the thought is you plant these plants where you have heavy metal contaminants or organic contaminants. The plants are able to take up those heavy metals, and then we remove the plants from the environment and we can take them and haul them off to be properly processed. So we're taking those heavy metals and contaminants out of the water system that way. So for me, bioremediation is really exciting, but it's also an inexpensive alternative to conventional cleanup strategies.